Hi everyone. So I'm Michal Čáp. I'm a researcher from TU Delft. I'm also affiliated with AMS, if any of you know what it is. And I do research in large-scale fleet management. So today I would like to show you how can be. So is this microphone working or this one? Both. Oh, okay. So today I would like to share with you how can be research in large-scale fleet management useful to get insights about how will our cities look when they are flooded with self-driving cars. So hopefully this, I feel bad for interrupting this very interesting discussion. Hopefully this will be relevant for the topic as well. So the reason why we are looking at, and many other people are as well, in algorithms for large-scale fleet management is the emergence of the idea of self-driving car. So as you probably know, there are multiple companies that develop self-driving cars, be it Waymo, Uber, Ford, most of the car manufacturers and others. And for most of them, the ultimate business model is to run fleets of cars and act as a mobility provider. So basically they want to provide a service from point A to point B that will be as comfortable as using your own car at a price that will be lower than using your own car. Now, if you think it's far, maybe you've seen in news that Waymo has just bought 60,000 of those cars to be converted to autonomous cars, plus to 20,000 Jaguars. To put it in perspective, I believe that in Amsterdam there is 300,000 cars. So that's basically 1/4 of a total fleet of cars that we have in Amsterdam. They will have it in the garage, and they will just come to some city and kind of put it there, and it will just act as a mobility of service system. Now, so this is coming sooner or later, and the cities, as we kind of have seen before, need to react to it. And now the question is, what does it bring us? Like, is it good news? Is it bad news? There's a lot of discussions. Most of the discussion is that we hear is qualitative. So yeah, you see arguments saying this is going to be like totally dystopian future. You see arguments that are kind of painting a nice utopian future where we get rid of all those parking, the cars that are parking on our streets, and we turn them in parks and bike lanes. So what we try to do, we try to make mathematical models of what can be realistically achieved with those large-scale mobility on-demand systems, so that we can make more informed decisions, kind of based on actual numbers, when we design our regulations, or when we kind of decide on what will be our attitude towards this new trend that we are seeing. I will use Prague as a use case because we collaborate with CTU in Prague. We have data from the city. And one of the first things that we did is that we tried to analyze this hypothetical scenario. We tried to see what would happen if we replace all private cars in Prague and the trips that people make in those cars by a system of self-driving taxis. And we want to design the system in a way that it provides the service at the same quality of service level as we have with our private cars. So but here the idea is that you basically have your car available in, let's say, 99% of the cases, unless it's broken, and you typically are able to have it ready in a few minutes, basically just the time it gets to where it's parked. So the first thing that we need to have to do such an analysis is we need to know how does the transportation demand of a city look. For this, we use a transportation demand model. It's a machine learning based model that fuses multiple data sources, such as we use questionnaires, traces of mobile phones, some demographic data plus some other data sources, and the model is trying to synthesize travel demand that has the same aggregate properties as the real transportation demand of a city. In the case of Prague, this corresponds to roughly 1 million of trips a day by a car in the city, and each trip is defined by origin, the time when you want to travel, and a destination. we take this data set and we try to design a system that would be good enough to serve this demand with satisfactory quality of service. So the way we do it is that we kind of imagine that there are stations, 40 stations kind of scattered throughout the city, and they serve as temporary parking lots, plus facilities such as recharging and cleaning. When you order a car using a mobile phone or some other device, it gets dispatched from the nearest station. It picks you up at where you are, and it will take you to your destination. And after it drops you off, it will return to the nearest station. It can serve other passengers. Now, if you design a vehicle sharing system, one of the hurdles that you have to face is that in cities the transportation demand is unbalanced. So there are typically dominant transportation flows. What it means that typically in the morning, most people want to go from residential areas to the city center, and there is only relatively fewer people who want to go in the other direction. What happens is that since the two flows are in balance, you will eventually have no cars in the residential area, and there will be too many cars in the city center. So the only way we can actually counteract that is to start sending the empty cars in the opposite direction. This is called rebalancing flow, and this is something that is very hard to avoid in any type of vehicle sharing system. That's something that people intimately know from all those bike sharing systems in Paris, Boston, and those cities where they do it in vans. So on the algorithm side, what we did is that we designed a model that allows us to compute what is the optimal fleet size that you need, and what is the optimal kind of cheapest rebalancing policy that is satisfactory to ensure with like a very high probability that none of the stations will become empty, meaning that every customer of the system has like almost 100% chance that if you want a car, you will get it. Then you feed it with the transportation demand data, and it will give you an estimate of how large your fleet should be and how much energy you spend on the rebalancing. So to kind of recap, we want to serve 1 million trips. Currently, we estimate that those 1 million trips by car in Prague are served by 300,000 vehicles. That's because on average, when you take a car, you do 3 trips a day. You do home, work, and sometimes you have like one errand on the way. You go to shopping, sports. So on average, just like 3 trips a day. If you want to serve this set of trips with a system of shared vehicles, you can do it with 60,000 vehicles, and this will give you kind of quality of system level of 99%, meaning that with 99% probability, if you want the car, you will get it. So this, you see it, the 60,000 vehicles, this is roughly 20% of the current fleet. So we are able to decrease the fleet size 5-fold. And moreover, because those vehicles are kind of busier, they park less, this will translate into even bigger reduction in parking space requirements. So that can go like even like one order of magnitude down to like roughly 20-fold reduction in like how much parking space you need. But you have to pay for it by the need to rebalance the vehicles, and this is a number that is sort of fundamental to the problem. When you compute it for other cities, you will get a very similar number. So in the case of Prague, you have to spend like 35% extra energy or extra vehicle miles traveled on moving the empty vehicles around. So that's sort of the trade-off that you need to make if you want to run a huge, large-scale mobility on-demand systems with single occupancy vehicles. Yeah.
35% more than the current system, or per vehicle?
In total. Total amount of vehicle miles traveled.
Sorry. Does that also happen when you start to do car sharing?
So this is without ride sharing. So single occupancy vehicles. Yeah. So these sort of metrics you can compute using an sort of macro level model where you only reason about flows between different regions of the city. We were also interested to look like what would be the impact on the utilization of the actual road infrastructure. For this, we switched to a micro-level simulation model, where we actually simulate like every single vehicle and every single passenger on a real road network of the city. Just to give you an idea, how does that look? Here you will see morning peak in Prague. This is roughly 50,000 vehicles. So the blue dots, the red dots are the passengers that are waiting to be picked up by a vehicle, and the green triangles that will be visible in a while are the rebalancing vehicles. So these are the vehicles that move from places where there's too many vehicles to places where you need them. You can measure what is the density at every road segment, and then do like analysis over this data. So then you can see like how would the utilization look compared to the current system. I don't know how well you can see it, but the darkness of the color represents the density at each road segment. So you can see that it's generally darker. The system when you use mobility, when you use kind of self-driving taxis, and you can easily explain it. So the utilization of every segment can be attributed to different phases, kind of life phases of a vehicle. So the first phase is that when it drives empty from the station to pick up a passenger. That's something that you don't have now. Then it drives with the passenger to the passenger destination. That's what we have now in current system. Then we have the drop-off trip. That's when the vehicle drives empty to the station. And then you have the rebalancing trips. That I explained earlier, and then you can look at where do we exceed the critical capacity. So this black color shows which segments would be congested if we deploy such a system and are not congested now. So this is like this shows where would be new congestion. Okay, so what we see is that we can if we have Uber coming here, like operating on large scale, they are right. They would reduce drastically parking space requirements, but they would like dramatically overload our road infrastructures. So that what that means? It means that either we'll have to massively invest into extending the existing infrastructure so that we can kind of handle this new load, or we would have to accept like much longer travel times. So one possible solution is obviously ride-sharing. So ride-sharing is the idea that you try to combine passengers that travel in the same direction into one vehicle. An interesting thing is that this is an interesting mathematical problem because it's not clear if you have like thousands of trips that you want to serve, which of them are the best to combine together. So that we formulated that as a mathematical optimization problem where we have a fleet of vehicles, we have a set of requests, each defined by a start and destination. We also have some sort of maximum prolongation that you are willing to cost to each of the travelers, and you are looking for the optimal assignment of those passengers to the vehicles such that some quality metric is optimized. So this is generally a very hard optimization problem because like all the
Ask Mars.
Is there a question?
You should talk to companies like, actually they're in the room, companies like Camera 42, who have great algorithms for solutions like this.
Yeah, so we also have a great algorithm.
So, work together.
Actually, I think
Find of the algorithm.
we believe we have the best one.
The biggest one.
Yeah, so this is generally known to be a very hard problem. So we came up with an algorithm that is based on idea that I don't know if I should explain. Basically, you generate groups of passengers that you want to serve. You formulate it in a form of a combinatorial optimization problem. You find the optimal assignment, and it will give you the optimal solution. The bottom line is that then you take this algorithm, you plug it into our simulator, and you try to see what happens. So this is the result. So the first picture is the current system. So you can see the current fleet size, 300,000. And the second picture is the system with shared single occupancy vehicles. The third picture is the system with shared vehicles that have a maximum capacity of 5. What you can see clearly is that the total number of vehicle kilometers driven in the system is actually I can use this I think. Goes down to 60% of the current state, so that reduces dramatically. This is, I mean, you can see it as sort of indication of how much can be done if everyone would be willing to share, right? So this is like really the optimistic scenario. So it's if you convince everyone to kind of be part of the system, this is how much you can achieve.
A communistic system.
Well, you can invent some incentives so that it's going to be like a individual rational choice. So you can see that you can reduce further the fleet size threefold, and more importantly, you can reduce the congestion and the total number of vehicle kilometers driven in the system, which also translates into pollutions or energy consumption of the system. So to conclude, I wanted to show you that there is value in using, mathematical models of those systems, because they actually give you numbers, and you can kind of see where do the trade-offs form. We have applied it as a case study in Prague. And you can see that the vehicle sharing, or sort of mobility on demand without ride sharing, is kind of prohibitive in terms of the requirements on the road infrastructure. So what we really need to solve here is to figure out some way how we can convince people to share more their individual rides, if we want to save all those parking spaces. Of course, there's a lot of things that can be further studied. So, for example, what we assumed in all those studies is that the demand will stay the same, which is unlikely, right? It's probably if you get a new form of transport that is cheaper than your own car, you don't have to drive, there will be more people who will want to take this form of transport. The other thing that you can do, you can try. I think that's an interesting. That's a point that was mentioned before. Those systems will be owned by one entity, so it could be some commercial company like Uber, or maybe better by, in Europe, by some governmental organization. But the kind of unique opportunity you have is that now you have control over the fleet, so you can actually coordinate the motions of the vehicles to avoid congestion in a much better way than you can do now with human drivers. Yeah, so that's what I wanted to share with you. If there are any questions, please.
Some questions?
I have two.
Two.
So one is more like, why does the car have to be exactly like, if you say 5 people have to be in a car, why does the car have to be a standard car with 5 seats? Can it not look differently? So it is more comfortable, because of course you don't want to be the person who has.
Yeah, certainly. Yeah. So this is an arbitrary number. Yeah. So that's something that we work on now. Is that, I mean, this is like a continuum, right? You can imagine, like, on one hand you have a private car, and on the other hand you have something like a bus. And
why choose a car?
And we would like to know, like, how exactly does the trade-off between the operation cost and the quality of service looks. Because there might be things like minibuses, 15-seaters, 10-seaters, 8-seaters, and there are probably areas where one thing is better than the other. Yeah, that's something we work on.
There's an assumption that cities want cars, but I think the future is a city without cars.
No, that's not the assumption. The assumption is that the cities want mobile citizens, and they want to do it in a way that optimizes the operation cost, so as cheap as possible and as fast as possible. But you can, there's trade-off. You can only pick a point on a curve.
But the car doesn't have to be the way we imagine a car
Yeah,
right now. So
that's totally correct. Yeah.
Something different.
Yeah.
In your model, you mentioned you started with a single occupant vehicle, but it looked like it took the space of a normal car, or am I wrong? It's not that they can be on side by side, for instance, or the size of a bike.
Oh yeah. So that was assuming that the vehicle looks like this, which is kind of the rationale behind that is that it's how current taxi service works. So you have a car that is a standard car, and mostly it has only one person in.
Yeah.
And in order to kind of put more people in, you would have to change many things, like a mindset of people, so that they will be willing to, share. Yeah.
Well, I was thinking the other way around. If you say it's we're modeling or calculating what would happen if there are only individual vehicles, I wouldn't imagine they are as big as a normal car.
That's right. So I think that's a good point. So they can be lighter, definitely. Probably more efficient more efficient. I wonder. So we probably have to work with some sort of automotive designer to tell us like how does the curve look exactly in terms of how much you save.
And how much does it mean for parking space or space on the road?
Yeah, this is a bit arbitrary as well, but a good point there.
Do you already have an idea how to motivate people to rideshare? Since we offer a service where we match colleagues to go that work that live close by each other.
Who's we for you?
Together in this.
Together?
Yeah.
That's the company name?
Yep.
Together.
Where we give huge incentives for colleagues to drive together if they live close by and go to the same office location. And even with big incentives, it's still hard to motivate them. So do you have any idea about that?
Yeah. We so this is interesting because I think I think that's something where designers can contribute a lot. And like many disciplines can contribute a lot. So what we think is that you can design economic incentives and cities. So my personal belief is that the most efficient way to make this happen is to introduce a congestion toll. So kind of a dynamic toll that would basically start increasing the price of a segment based on its kind of popularity, let's say. And what would happen is that you would pay per kind of square meter and second that you use the segment, and that way it would be just beneficial for you to kind of travel together with a neighbor, for example, or even better, use a service that does it in some sort of centralized way. So that's one like very system level futuristic maybe vision.
Carpool lanes work.
Carpool lanes they work. I think they so first of all, congestion tax it provably works. So in Stockholm, in Singapore, they have that. I mean, less simple, much more simple system. You have to pay a little charge for entering the city in peak hour. Like in Singapore it's like €2. In Stockholm I think it's €2 if I'm not mistaken, and in Singapore I think it's even dynamic, and it does improve the travel times through the city center. And carpool lanes, I think they do work. In some sense. So basically, because I think they are fair because you use the infrastructure more efficiently if you car share or if you use a bus, right? So it's a good way to kind of pay back. No.
Final question?
Well, it's all a matter of convenience, and actually that company, Newtonomy, which is an MIT startup, started like 3-4 years ago.
That's.
They have a vast amount of experience in Singapore. That's the interesting company. What is so striking?
I work with them.
What is so striking about Waymo? That was your first slide. That is, they make the completely wrong decision to invest in the Chrysler Pacifica, which is a 2.3 metric ton weighing vehicle That means that every time it goes on the road, it carries the load of approximately 28 passengers without even moving passengers. And it has batteries on board, but it has only enough battery power to cover the first 30 kilometers. So that's the complete wrong decision at Waymo. And that's actually very interesting because Waymo came from Google. But Newtonomy is the most, I hope you agree with me, is the interesting company.
Tell them.
Yeah, I'll tell them. Yeah, so I think that this is just like a sort of intermediate step. So I guess in future they will, all of those companies will invest into those sort of efficiencies. It's just that they want to develop their own platform right now. That's what I feel.
But they're actually also the furthest in autonomous vehicles because it's small enough to function as an autonomous vehicle. And the Chrysler Pacifica is a ridiculous big vehicle, will never function autonomously.
Yeah, I'm not sure if they would. Yeah, this is debatable, I think.